Good afternoon, everybody. It's my great pleasure to be here and to present our paper. My name is Željko Božić, and my former student Iva Rački, she's just coming here. And we are going to present an interaction model for multiple propagating fatigue cracks. I heard just one keyword from Professor Besson 3 minutes ago. Is there any crack interaction? So I will talk about this, about propagation interaction of long fatigue cracks. And we are coming from the University of Zagreb, founded in 1669 as the biggest university in Croatia. And this is our faculty, recently renewed, now it looks better. And just to show you what we are also doing, we are organizing nice conference, and I will tell you a few words more at the end of this presentation. So here is the outline. I will give a short introduction, then we will speak about multiple site damage in thin wall structures and fatigue crack growth, present results of fatigue crack growth tests, then finite element based fatigue crack growth models, and will present in more details analytic model for modeling interaction of multiple propagating cracks. We will compare experimental and simulation results and will draw some conclusions. So cracks may initiate at sharp notches, growth or sites of stress concentration due to geometrical discontinuity. Several cracks initiate in a line, so-called multiple site damage is generated. It can eventually lead to crack collisions, creating large-scale damage. Thin wall structures such as aircraft and ship structures are prone to fatigue, cracking, and multi-site damage or multiple cracks. Professor Željko from that nicely shows stages in the fatigue line. So we declare initiation period and crack growth period. And here we speak about crack growth period, about growth of large cracks. So as you know, we can do experiments and obtain the crack length with respect to number of cycles. And then from this we can design crack growth rate diagram. And from this diagram, we can assess, for example, Paris equation constants or any other power law constants. So what is multi-site damage? Fatigue cracking examples. Here we see a Loka Airlines Boeing 737. This accident occurred in 88 or 89, I don't remember. So what we have here, we have at the upper rivet row initiated cracks at the rivet locations. And then on the surface, loading cycling under cycles which are caused by landing and taking off. Cracks are initiated, they propagate, they collide, and in this case, large-scale damage is generated. Similar situation we have with ship structure. What you can see here, this is the deck structure turned upside down, and you have different panels in longitudinal directions, and you have also bulkheads every 5 meters. So these details are produced by welding. So there are stress concentrations due to geometrical discontinuities and residual stresses. And cracks initiate here, similar as the Aloha example, in several occasions. Basically, fatigue is multi-scale fatigue phenomenon. So we can assess some parameters like critical resource shear stress on atomistic level and use them on micro scale level as the input data to, for example, Tanakamura model and assess fatigue life to crack nucleation. And after these cracks become a little bigger, like 1 millimeter or longer, then we have different way of propagation. Then we have long fatigue cracks, for which we use then some power law models on, for example, Paris equation. So I'm showing one paper which was published in 2014 in Fatigue and Fracture Region Material Structures. I think Professor Kong is not here, he is the editor chief of the journal. And now we come to our specimen. You can see here a panel which has, we have two kinds of specimens, one panel with one crack and one panel with 3 cracks. So P1 is specimen with 1 crack and a single crack, and P3 is specimen with 3 collinear cracks. Material is mild steel with yield strength 235 megapascals, tensile strength 400 megapascals, elastic modulus as shown here, and also ratio. So in the net section, we have 80 megapascal. We have 80 megapascal nominal stress. And for this, we need this force, which is shown here. And stress ratio was slightly above 0. Crack details were, as given here, half length was 8 millimeters and total crack length, initial crack length was 8 millimeters. And then we have carried out experiments, and what you see here is fatigue life of P1 specimen with 1 crack. It reached like 2 million cycles, and specimen with 3 cracks reached 1,200,000 cycles, almost 1 hour. See that it's very big difference when you have multiple side damage. When it cracks, fatigue life is much shorter. And this is what we obtained or analyzed experimentally, and we want to simulate this. And for this, we will use Paris equation as shown there. And as mentioned before, we generate a crack growth rate diagram, and from this we obtain constants like C and M as shown here. And basically we have here mode 1 opening, only mode 1. And this is how we look at this program. The cyclic loading, we have crack extension for each cycle, some delta A, and then use Paris equation to simulate this. And this is our specimen P1 with 1 central crack. And to simulate this, we can use Paris equation, but we need stress density factors. So they can calculate them analytically, but it's better to calculate them numerically. And from crack array diagram on the right side, we can obtain this equation here, you see, which is called Paris equation. And if you write this equation in another way, we can calculate number of cycles needed to propagate for some initial crack length is 0, some final crack length. And this is very fine, we all know this. And if we are not limited to Paris model, we can use modified Paris equation and consider
delta K effective, that's so-called Lucas model, or we can see the J integral, cyclic J integral, effective J integral. We also can consider CTOD, and in multiplicative quadratic mechanics, CTOD and J integral are correlated. So for our specimen, we have our specimen here. So we can consider only 1/4 of this specimen in finite element, and that is due to double symmetry. And this is what you see here, 1/4 of the specimen, and this figure shows, the zero shows stress density factor range with respect to crack length, with respect to half crack length. So we have K now, and we have K as not as a function, but as a discrete points. So we will integrate this equation numerically. And basically what we have here, we have a straight line between two points for which we calculate K. So piecewise linear curve for which we calculate the stress density factor by 5 method, and we will integrate this equation directly. So stress density factors calculated for P1 specimen shown here, and that's very easy to do for one specimen with a single crack. And then we have experimental results like 2 million cycles and simulation results, and simulation fits very well to some 30 millimeters crack length when we are in pure Paris region. And then we have some statistics done the experiment of constant back propagation, and simulation is still using this according to this model which we use Paris. And so this is what I just mentioned. And for specimen 3 cracks, this is experimental result, and we want to simulate now. We want to simulate fatigue life, but basically 3 cracks, and then it comes what I mentioned at the beginning, what also Dr. Son mentioned, interaction of this. How can we model interaction with this? You can use to the extended finite element method when you use that. And sometimes that you don't have everything under control, but you have an analytical model which is perfectly under our control, and we will learn how it works. So this is basically the one crack before the experiment and after the experiment. And so this is 1/4 of our specimen. We have 3 cracks, but due to symmetry, we have only 1/4, and we can basically have 6 crack tips, but due to symmetry, we consider only 3 crack tips, 1, 2, and 3. And so we show them this here. What do we do? Well, at first we should assume initial crack length, and we have taken this from our experiment. The cracks were long and this and that. So we started from, we had experiment, then we simulated and compared with this later with the experimental result. So we have to take one crack tip as a reference. So this is in this case tip 1, and this is it. And for other 2 tips, then we should see how do they interact. And so this is what we have as a first one from our experiment. Then we give some initial increment for the reference active, and then we assess increments for other 2 crack tips by using Paris law in this way. good way to do it. Then we have this assess increment for crack tip 2 and crack tip 3. And then we have to check, is it good or not? How do we check this? We will calculate delta effect by opposite way. Now we don't calculate number of cycles, but we calculate propagated crack length. So we do this for A2, so for tip 2, and for tip 3. And then this is a better, it is better. This, and we should repeat these steps until we receive convergence. If we receive convergence, when this difference between assumed and calculated crack length is less than some limit which we give there, some tolerance. And then we repeat this. We repeat this, and when we reach some final crack length, this final crack length can be determined by if fracture will occur if a crack reaches our critical crack length. So, some crack length before fracture occurs. Yes. And then we show results what we have achieved. So for these 3 cracks, we had stress density factors ranges shown there. Then we compare simulation results with experimental results. And you have this big circle for tip 1 and circles, small circle for average crack length for tip 2 and tip 3. That's for the experiment. So the big circle and the small circle. And then we have simulation results of rectangular marks. You see that for initial crack lengths, where our solution we have very nice agreement results. And how do we know that what we have simulated is good or not good? We have taken as a reference crack tip 1. So we will repeat the simulation, we will take another crack tip 2 as a reference. And then we'll compare these 2 simulation results. And what you see for simulation results with the reference crack tip 1, we use diamond marks, and reference crack tip 2, we use triangle marks. And so we have tip 1, tip 2, and tip 3. And if you look carefully here, the simulation results overlap perfectly. So it's telling us that our simulation procedure is really fine. This is what I wanted to show you. This analytical method for taking into account interaction of multiple propagating crack tips. We can do more examples. Some cracks can be longer and others shorter, and again to see this interaction. So basically, there is no interaction if these cracks are far and if they're short, if they are short. But if they are big, then there is very strong interaction. Different crack propagation life of especially with a single crack and multiple side cracks were studied. An incremental simulation procedure for multiple propagating crack is based on a fatigue crack law model. In this case, used by this law was introduced and implemented to fatigue placements with 3 collinear cracks. An independent procedure can be applied to fatigue-like simulation of built-in wall structures, such as ship structures or airplane structures, offshore structures, and other structures, and use for matrix inspection schedule planning. And as I showed you before, we are all kindly invited to learn in Dubrovnik in next year in August from 14 to 14. And for the conference and before the conference, we cover the summer school, fatigue culture, modeling the analysis. On 10/11, that's Monday and Tuesday, and the conference. We have welcome on Tuesday evening. That conference is running from Wednesday to Friday. Usually have like 100 participants, but now we expect more. Because we will organize an open thematic symposium for different authors, they bring and gather their colleagues. And two papers are regularly published in Procedia and Analytic Journal. And for this year, conference already in analysis journal submission is possible, it's open. And procedure is almost closed. We are sending this relatively for this year conference.